All right, so it looks like appears to be working, I hope. So, like substitution, there are two limiting cases. For elimination. Right? So elimination can be E1, which has a unimolecular rate determining step and first order observed kinetics. All right, so that 1 stands for the molecularity of the rate determining step and for the observed reaction order. And then we also have E2, right, which is bimolecular rate determining step. It is in fact a concerted reaction, which means everything's happening at once, bond breaking and bond forming at the same time, and it has second order observed kinetics. So it probably comes as no surprise that the one that's concerted, where everything's happening at the same time and has the second order observed kinetics, that's the one that has stereochemical requirements. And there must be an anti-periplanar geometry or relationship between the hydrogen that is removed and the leaving group. Right? There's no such stereochemical requirement for the unimolecular pathway because the unimolecular pathway goes through a carbocation intermediate. Right? In fact, the same carbocation intermediate that the SN1 unimolecular substitution goes through. So the first step, which is the rate determining step for E1 elimination, is identical to the first step for SN1 substitution. Knowing that, it probably doesn't surprise you that when you have an SN1 substitution, you often have an E1 elimination as a competing pathway and vice versa. So SN1 and E1 tend to occur simultaneously, and which one dominates is going to depend on how strong the base is. Right? So there is a stereochemical requirement for E2. There is no stereochemical requirement for E1, just as there is a stereochemical requirement for SN2 and no stereochemical requirement for SN1. But there's a new complexity for elimination because there can be multiple types of adjacent hydrogens. Right? Removal of which gives structural isomers. And that can result in regioselectivity. So when we talk about stereoselectivity, we're talking about one stereoisomer being formed in larger quantities than another stereoisomer, right? Because of the activation energy difference. When we talk about regioselectivity, we're talking about one structural isomer being favored over another structural isomer because of activation energy differences. So mechanism, right, for E1, if I just start with kind of a random molecule, I'm going to show the leaving group here. Let's use bromide, why not? Alright, so that's a fairly simple example. That's just 2-bromo butane and that's the R isomer, the way I've written it, right? Bromine is number 1, ethyl beats methyl, right? So the mechanism, same first step, start the arrow at the middle of the bond between carbon and bromine, because that pair of electrons is going to become the 4th lone pair on the bromide. Goes through a carbocation intermediate, the methyl group is now in the plane, right? The hydrogen is now in the plane. Planar carbocation, positive charge on carbon. But now if you have a base in there, if you have hydroxide ion, for example, instead of hydroxide ion attacking this carbocation, hydroxide ion is going to take off one of the adjacent hydrogens. So if I want to show the rest of the mechanism, I need to show those hydrogens. So I actually need to draw the adjacent carbon in its full dashed wedged glory, as well as this carbon, which I didn't have to do for the SN1 pathway, right? Because the SN1 pathway, this hydroxide was going to attack that carbon. So now I've got hydrogens here that are on a methyl group, but I've also got hydrogens here that's on an ethyl group. So one thing that could happen is this hydrogen could pluck that, this hydroxide could pluck that hydrogen off. And you'll notice what's happening here is this pair of electrons that used to be the carbon-hydrogen bond is going to become the second bond between these two carbons. It's going to become a pi bond. So I have it pointing to the center of that bond. And that will result in a double bond. Oops. Maybe I should avoid Texas carbon. Right, so that will make a double bond here. And you'll get one butene. But I could also take one of these two hydrogens off with hydroxide. Right, so pull that hydrogen off and take this pair of electrons and push it in there to form a pi bond. And that would result in 2-butene. And I could actually have both stereoisomers of 2-butene, right? Depending on which one of these two hydrogens I take off, I can get cis-2-butene. But I could also get trans-2-butene. So I've got 3 possible alkene products that I can generate through the E1 elimination. The energy diagram is going to look a lot like the SN1 energy diagram. We're going to have that carbocation intermediate formed, and then we're going to have 3 different products, right, going over 3 different activation energies to get to those products. And those reactions are happening simultaneously, so I've got 3 different activation energies. So which of the products is most stable? 1-butene, cis-2-butene, or trans-2-butene? What order should I put these in?
Would cis be the most stable?
The cis is the most stable. So why? What sources of strain?
Substitution.
What's that?
In the video, you explain it as substitutions. Did you mean hypoconjugation when you would say that?
So hyperconjugation is the reason why the 2-butenes, both of the 2-butenes, are going to be more stable than the 1-butene, right? 1-butene has less hyperconjugation. That was my next question, so you've answered that one instead. Right, so 1-butene is going to be the highest energy. More substituted double bonds are more stable because you've got more hyperconjugation, so you're donating extra electrons into that pi bond, and the pi bond is a little weak anyway, so anything you can do to increase the electron density of the pi bond is going to make that bond stronger. Right. So that was my next question, is which is more stable, 1-butene or 2-butene? We've covered that. So within the 2 butenes, is there a source of strain that might cause one of those to be more stable than the other?
The trans is going to be more stable.
Right, why?
Because there's steric strain when you have the methyl groups on the same side.
Yep. So that makes the cis isomer less stable. So if we want to assign major or minor, we would say that the major product is trans 2-butene. The minor product is cis 2-butene. And the 1-butene, we probably only has traces. Right? That's stereoselectivity. Because these two are stereoisomers, but that is regioselectivity. Because these are structural isomers of that. Right? So we've got both stereoselectivity and regioselectivity going on in this situation. Right? Hyperconjugation is the reason for the regioselectivity, and sterics is the reason for the stereoselectivity. Since the unimolecular pathways are generally under equilibrium conditions, we get the products depending on the stability of the products. Right? For the E2 elimination, we're going to get the products based on the stability of the transition state. And that's going to be a little bit different because there's that stereochemical requirement that there isn't, right? We can take any of these hydrogens, there's 3 hydrogens here and 2 hydrogens there. We can take any of those 5 hydrogens off from this planar carbocation. There's no requirement that the hydrogen has to line up or not line up with the p orbital. For E2, things are a little different. For the E2 elimination, if I start with that same material, make sure I do start with that same material. Right now, the way this molecule is written, I can't actually do elimination at all because I don't have a hydrogen that's anti to the bromine. If I were to draw a Newman projection for this, right, and put that bromine in the back, what's anti is the CH3 group. Right? So neither of these 2 hydrogens can be removed until they're put in this position. So I actually have to rotate that molecule to get a hydrogen up here. In order to do the elimination. So now I can take this hydrogen off with my hydroxide ion. I can form the pi bond and I can lose the bromine all at the same time. And since this is concerted, I'm actually forming 2 bonds here. I'm forming a bond between hydrogen and oxygen. I'm forming a bond between carbon and carbon to make the pi bond, and I'm breaking a CH bond and a CBr bond at the same time. I want to show the transition state. There's a delta minus on there. We're forming a bond to hydrogen and breaking that bond to carbon. I'm forming the pi bond, and I'm also breaking this bond. So break, form, break, form. Right? 4 bonds are involved in the transition state. And then that product would be the cis-2-butene if I took that hydrogen off. But I could also have rotated this to take this hydrogen off, in which case the methyl group would be back and the hydrogen would be up, and that would generate trans-2-butene. So there are actually going to be 3 different transition states possible. If the base is unhindered, my product distribution is the same as it would be for E1. Because hyperconjugation is going to stabilize the partial pi bond the same way it would stabilize the full pi bond. So the transition state energies are going to be in the same relative orientation. If, on the other hand, the base is very hindered, and the classic examples of very hindered bases, there are 2 that you'll see over and over again. One is the tert butoxide. This is potassium tertiary butoxide. And the other is lithium diisopropylamide. If the base is very hindered like these 2, right, we've got lots of steric bulk, which makes it hard for the base to get to a hindered hydrogen, then the most accessible hydrogen is the one that's removed. And the least substituted alkene is the major product. Right, so if I were to switch and use one of these bases instead of hydroxide, then I would get as my major product 1-butene, and as my minor product the cis-2-butene, the trans-2-butene, and then my traces would be the cis-2-butene. You have to be a little bit careful though, because sometimes that's not a CH2 group, right? There's not 2 hydrogens on that adjacent carbon. And if there aren't 2 hydrogens on that adjacent carbon, I have to get a very specific, right? If one of these was something other than hydrogen, there'd only be one way I could rotate that in order to get a final product. So sometimes you get just a single product. Right, so if I had a secondary leaving group, something like this, oops, making a mess. Supposed to be bromine, sorry. Right. So I have to make sure that this hydrogen and this bromine are anti. Right. So only one possible geometry around the double bond would be possible for this product, right? I could only get the one where the CH3 groups were on opposite sides. Because I've lined it up so this hydrogen is in the front and the bromine's in the back. The CH3s are on opposite sides. But the other product, which would have the CH3s on the same side, is not possible. Because there's no way that I can rotate it so the 2 CH3s are on the same side of the molecule that still puts this hydrogen anti to the bromine. Right? So not all products are possible. which is good, right? If we're doing an E2 elimination, sometimes we would like to have selectivity. So in an unhindered base, right, I would get this as my major product. With a hindered base, I'd actually go this way, right? Because this hydrogen is going to be hard to get at because of the steric hindrance from the phenyl group and the methyl. So the hindered base goes here, and an unhindered base goes here. So you've got a little bit more complexity for elimination reactions than you have with substitution reactions because of the possibility of forming multiple structural isomers as well as multiple stereoisomers.